OK, so we've talked about structural hazard, or we've talked about pipelining basics. And now we're going to go into the three main types of hazards: structural hazards, data hazards, and control hazards. Let's start off by talking about structural hazards. OK, so let's overview structural hazards here. So structural hazards, as I said before, occurs when two instructions need to use the same hardware resource at the same time. And there's a couple approaches on how to resolve this problem. I mean, we can't just throw up our hands and just stop the pipeline, or maybe actually that kind of is one of the solutions. But you need to somehow think really hard about how to deal with a structural hazard. One thing you can do is you can explicitly avoid having different instructions that would be in the pipeline at the same time use one structure at the same time. And you can do this by the programmer, or maybe the compiler can do this. Next way to go about doing this is you actually have the hardware take care of basically all of the problems. And there's some complexities in actually building this, but you want to stall the processor, or stall a portion of the processor, or stall the dependent instructions. Or excuse me, you stall, let's say, the earlier one when you go for the contended resource. So a good example of this is if you have one resource, two things are trying to use it, you have a priority encoder in there, and the priority encoder says the earlier instruction gets to use that, because if you sort of invert the priority order, you might end up with deadlocks. Another good way to do this is you actually can duplicate the hardware resources, or you can add more ports to a memory structure, which is sort of the equivalent of duplicating the hardware resource. And this is, to some extent, a solution that is used pretty widely in something like the MIPS pipeline. The basic 5-stage MIPS pipeline is we actually duplicate certain resources. For instance, there's two memory arrays. There's an instruction memory array, and there's a data memory array. And we'll look at an example where those two things are together. But the simple 5-stage MIPS pipeline was really designed not to have any structural hazards. And the ISA was basically designed for that to be the case. But more complex instruction sets and pipeline designs, you might have to deal with something like a structural hazard. And even if with the MIPS ISA, if you go to deeper pipelines, you might end up with structural hazards. And we're going to talk about that now. OK, so the first thing we're going to talk about here is structural hazards if we want to unify the memory. So as I said in the 5-stage MIPS pipeline, you have all the hardware you need for every stage, and all the stages are basically independent. But let's say we were to modify this and instead have one memory here, and we wire out, and we only have one port into this memory, so only one thing can access the memory at a time. And we wire the program counter into here to be able to fetch our instructions. We wire the data out up here into the instruction register, so it's just wired in the same place as the instruction memory was before. And we take where we had the data memory access when we want to do a load or a store, and we run those wires down here, and we put a multiplexer here to share the address. And only one of these resources can use it at a time. OK, well, let's draw the pipeline diagram for what happens with something like this when you go to execute a load instruction, we'll say, on a unified memory architecture. So if we take a look at this structural hazard example where we have a unified memory, where we have the one memory here, which is replacing both our instruction memory and our data memory, we need to walk through, let's use this as an example to walk through the pipeline diagram of how instructions would flow down this example here. So let's start off by executing something like a load first. Then let's say we have an add, followed by an add, followed by an add. OK, so this is our first pipeline diagram here. We're going to have the load coming down the pipe. And it's going to execute, or it's going to enter the fetch stage. Then it's going to go into the decode stage. Then it's going to go into the execute stage. Then it's going to go into the memory stage. And finally, right back. The first add comes down here, and it's going to go into fetch. So you go into decode. It's going to go into execute. It's going into the memory stage. And finally, you go to write back. The third add is going to come down the pipe and go into the fetch stage, decode, execute, memory, write back. So far, it looks like a pretty idealized pipeline. This next add, maybe we should just put an F here. Let's think about this. Is this right? Can we have an add fetching from our instruction memory at the same time as a load is accessing the memory, this unified memory that we have here? And this is the question. Is we have this unified memory, and we're trying to have two things accessing it at the same time. And this is a structural hazard. We can't do this. So instead, we're going to put a dash here, and we're going to somehow either stall or bubble or no-op this add for a cycle. And then we're going to use the fetch. We're going to use the instruction memory on the subsequent cycle. And the reason we stall the add and we don't stall the load is because this is an earlier instruction than this. This is a later instruction, and we want the earlier instructions to finish first. Otherwise, we might have some deadlock concerns or deadlock problems. So now we fetch, we decode, we execute, we use the memory, and we write back. And you'll note here, this gets pushed out one cycle because we had to stall here at the beginning one cycle. And this memory and this point here is the structural hazard that we saw that we had to resolve. And in this case, let's say we stalled one cycle to resolve that hazard. So now that we've seen how to do a unified memory and what the pipeline should look like for that, let's go on to a different example here where we have a two-cycle memory. And this two-cycle memory, we're going to have stage M0 and M1. We put a pipeline register down the middle of our memory here, but only one thing is able to use that memory at a time. So let's briefly draw the pipeline diagram for something like this. OK, so the second add is going to start flowing down the pipe, and it's going to be in the fetch stage, decode, execute, M0, M1, write back. Then we're going to have the load. We're just going to go fetch, decode, execute, M0, M1, write back. And now we're going to see a structural hazard. We're going to have this second load here is going to fetch. It's going to go into decode. It's then going to go into execute. Now here is the problem. If we were to put M0 here, what we see is we actually have two different instructions in time wanting to use one resource, the memory. So we need to solve this somehow. Now, how do you go about doing this? Well, there's different approaches, and we'll talk about that in a minute. One approach, let's say, is you could actually stall the pipeline here. So that was one of our solutions, is you stall the pipeline. So we're going to put a dash here to mean we stalled for a cycle. And then we're going to have M0, M1, and then write back. And you can see that it's basically pushed this instruction back one cycle. But this doesn't happen with other instructions. And the other thing to note is it doesn't happen if you have something like an add after a load here, because that's going to go fetch, decode, execute. Oh, sorry. It stalls here too. Execute, M0, M1. And these can be overlapped because we don't actually have any hazard in this case, because there's not a loads, or two things are not trying to use this memory at the same time. So you won't end up with a hazard there.